The next one is the Kfold cross validation. Kfold cross validation is the type of cross validation in which you split the sample into k equal sizes or k equal subsamples. Let's say, and the k can take any number. Okay, it can take 1, 2, 5, 10, any number. In a sample, let's say there are n observation, and you have taken k subsamples. So the number of samples or number of data points in each sample would be n by k, n upon k. Okay, so each subsample should have the equal number of observation or equal number of data points. Say for instance k equal to 5. So what you do is that you divide the entire sample and into 5 subsamples, each having n by 5 n upon 5 data points. Okay, and you just take one of the subsample as the validation set, and the rest of the 4 take as the training set, like the way we have done here. This is a training subsample, training subsample, training subsample, but the 4th one is a validation one, and then you take the 5th one as a training sample. So we build a model by using the data for the training samples and use the validation sample to validate it. Okay, so how do we validate it? The way we did in the in the previous slide. We'll use the same root mean square root mean square error. If it is a regression problem, if it is a classification problem, you can actually use accuracy rate to see if it is consistent across validation and training sample. Now that's for one iteration. You have to do it for 5 iterations, because the number the validation sample can be any one of these 5 samples. So this is the 4th one, the 4th subsample is the validation here. You can actually take the 5th subsample as the validation as well. Just change it. Okay, this has become validation and this is training. Okay, so now you build a model by including training samples 1, 2, 3 and 4th one, and then you validate on this particular one, the last sample. Okay, and you keep on changing that, right? So there will be 5 iteration. Validation sample could be this one, this one, this one, or this one, and this one, and every time you will get an error rate, right? When you validate your model, you will get some sort of a error, right? It could be any of these error, pure modulus of the error, or you're simply squaring it and taking the square root. You are actually using the root mean square error rate. So you will get some sort of an error while doing the validation for each of the samples. So the prediction error would be just the average of the error you are getting for each validation set. So if I have k validations, you will get k errors, and you just divide that by k, you will get the average error, which is your prediction error. Okay, so that's called Kfold cross validation. Normally people take the k to be 5 to 10, because otherwise it takes a lot of computational time to do all these iterations, right? So here it's 5 subsamples, so we have just 5 iterations. If it is more, it would take a lot more time. The advantage of this particular method of cross validation is that it doesn't matter how the data gets divided. Remember, in the hold out sample model cross validation, we had the problem of how we split the sample. If you change the splitting pattern, you probably get a different result or different prediction error. But in Kfold cross validation, it doesn't matter much. So that selection bias will not be there. Selection bias will not be present. Why is it so? So let's go back and understand why is it so. Now remember, in holdout sample cross validation, so the validation set that you are taking is completely different from the training set, right? It's completely different. The data points in the validation set will never be present in the training set. So that's the that's the criteria for holdout cross validation. Whereas here in this case, the validation set is, or the validation subsample is actually changing. So every sample, every data point would be part of training sample and part of validation sample, right? Because validation set can be this one, can be this particular one, can be this split as well, can be this split, and this split. Similarly, a training set can also be, all the splits. So every data point present in the sample will be a part of training data and will also be part of the validation data. Hence, this particular way of cross validating is free from sample bias or selection bias. The next one is the leave one out cross validation. It is a